Good morning. This is Mark Summers from Summers Technical Services. We're going to go through some lecture notes. I won't be able to be in class today, but I was going to finish up this Chapter 2 lecture notes and allow you to finish up the homework assignment that's due next week. So let's take a look at the lecture slides and see where we left off. So I believe we got through this first part talking about stress strain curves and talking about all these points on the curve to identify on our stress strain curve their material properties we learned about last time. Hooke's law, the equation, and the talking about ductility and brittle materials, ductile and brittle materials, how they behave differently, and we have to handle them differently. We start doing failure analysis later in the semester. We talked about yield points. Some materials have yield points well defined. Some of them we use a 0.2% offset rule to calculate them. And some materials, like the ones on the right, have no well-defined yield strength. Talked about different types of loading. Repeated loading causes fatigue failure. And again, we'll learn more about this later in the semester. Different load types we talked about. Stress SN curves that define fatigue strength and whether or not a material has endurance limit or not. And we talked about elastic deformation. We talked about Hooke's law again. We developed the equations, and we can come up with equations for elastic deformation as long as we're below the proportional limit. Based on Hooke's law, we can calculate elastic deformations due to loads on tensile specimens. And we had a couple examples we went through. So here's where we left off. So now we're going to talk about temperature changes. There's a material property just as necessary as yield strength and ultimate strength and Young's modulus called the coefficient of thermal expansion. And so it's a material property. It's different for different materials. And it's the rate at which the material grows or shrinks due to a change in temperature. And so the definition of this material property is alpha. It's defined as the change in length divided by the original length times the change in temperature. And so the units are 1 over degrees F or 1 over degrees C. There's two types of thermal expansion. You can have unconstrained. Unconstrained thermal expansion means the material just grows or shrinks due to temperature change, but there's no induced stresses involved because there's nothing constraining it from growing and shrinking. However, normally you've got materials, you got a part that's in an assembly, it's not free to grow or shrink unconstrained, and that causes constrained thermal expansion, and that's going to produce, turns out, very high stresses potentially, and so that's going to be something we're going to look at as well. So we can start off with our normal definition of strain, change in length over length. We'll put in Hooke's law, and then we use equation from the last sheet, and we can work our way down to the bottom. This is just algebra going from the top to the bottom. And if you've got a constrained situation where the part is heating up or shrinking and it's constrained so it can't move, then you're going to induce these stresses. And then the equation at the bottom will tell you what that normal stress is. It's going to be Young's modulus E times the COTE, coefficient of thermal expansion, times that change in temperature. And you'll get an opportunity to do a couple of homework problems calculating this. Okay, the next topic is Poisson's ratio. It is a material property that is defined as the negative of the lateral strain divided by the axial strain. And so I like this picture in the corner at the bottom. And mu is the Greek letter that is used to identify Poisson's ratio. So if you start with a material that's the green shape, and then you pull on it, most materials will elongate along the direction of the force, and it will contract in the other two directions. And so I've got a delta L axial direction, and I've got a delta L in the two lateral directions. And so you can calculate the Poisson ratio doing testing by doing a tensile test. And the values are going to be, mathematically, they can't be less than -1 or more than positive 0.5. Some typical values, about a third for aluminum and steel, concrete a little lower, plastics have a little bit larger range. But this is the material property you just look up in a handbook somewhere and to use for calculations when needed. So that defines another material property we need to know about, which is Poisson's ratio. An interesting combination of parameters now. We know about Young's modulus, or elastic modulus, which is E. We're going to define, so E, Young's modulus, is defined as the normal stress divided by the normal strain, sigma over epsilon. There's another material property that is shear modulus. Shear modulus, similar to elastic modulus, but it's shear stress divided by shear strain. And so we already know that tau we use for shear stress, gamma is shear strain. And instead of thinking about the change in length due to axial loads, this is the shift, the change in angle when you get shear loads. And so similar property, but has to do with shear stress as opposed to normal stress. And it turns out three very important parameters, elastic modulus E, shear modulus G, and this Poisson ratio we just learned about, are all related to one another in this equation at the bottom. You can write is shear modulus is elastic modulus divided by this quantity 2 times quantity 1 plus Poisson ratio. And so what does that mean? That means if you want to know E and G and nu, Poisson ratio, you only need to know 2 of the 3. If you know 2 of the 3, then you can calculate the third one using that equation. And this is for isotropic materials. There's more complicated equations when we get into anisotropic materials. But for now, we're going to be worried about, only concerned with isotropic materials, which is a lot of materials that we use in engineering design, like aluminum alloys, steel alloys, titanium alloys, and such. So those are important equations to use, and we'll use those same equations in doing some calculations, not just in this chapter. When we get to chapter 3 on torsion, shear stress due to torsion, we're going to see that shear modulus, capital G parameter, come into play. Okay, the next topic is, I think this is the last of the part 2 of the chapter 2 notes, is talking about stress concentration factors. So we've got this example, we've got this shaft, and it's got a discontinuity. Up till now, we've had bars that are constant cross-section all the way through. We've got examples here where I've got a cylindrical shape on the left that's got capital D diameter, and then it reduces down to a smaller diameter, in this case little d diameter. And there's a fillet radius r, little r, in between those two. And the plot at the bottom is very informative, and let's see if we can understand what's happening. So in the x direction, this is the location along the length of this shaft. And what it's plotting here is the normal stress in this shaft as I go from left to right. So you start over here on the left, it's sigma 1, and it's constant. I've got a force on each end pulling, and so the normal stress sigma 1 is just going to be this force divided by the area of this left end over here. So that's sigma 1. And I go over to the other side over here, and this is the stress sigma 2, we're going to call the nominal stress. And it's also constant over here, but it's much higher than sigma 1. We've got the same force, but we're dividing by a smaller area. So sigma nominal, or sigma 2, is bigger than sigma 1. However, right here during this transition, we get this spike here in the stress. So the stress accelerates and goes up very high above the nominal stress over here, right at this geometric deviation where the geometry is radically changing quickly. And we get this peak right here, and we're going to call this sigma max. This is the maximum stress in this part, and it's going to be the nominal stress, which is the stress over here on the smaller diameter, times something we're going to call a K factor, stress concentration factor. And so for this case here, depending on this little r value, this K factor is going to change. And so important thing to remember about the stress concentration factors is that the K factor is only a function of geometry. It has nothing to do with the forces or the type of material. It only has to do with the geometry. And we'll see that when we look at these charts that let us compute K factor. You'll see the only thing that matters is the geometry. So you can see we really have to take into account these stress concentration factors because the maximum stress is way larger than these nominal stresses. So stresses over here are just force divided by area 2. The stresses over here are the same force divided by area over here on the left side. As we get to the middle, we have this really spiky peak here you have to compensate for because this is going to cause failure. If this thing is going to fail anywhere, it's going to fail right here at this discontinuity in the geometry. Okay. So here's how we calculate this equation from the last sheet. We calculate the maximum stress by multiplying the stress concentration factor by the nominal stress that we calculate on the small diameter. So the nominal stress is the stress that would occur if the geometry remained constant. There's no abrupt changes. Stress concentration, like I said a minute ago, is a factor of geometry only. So, and then there's some figures in the textbook that let you figure out what these K factors are. So here's one of the charts out of the textbook. Here I've got an example. It's a plate with a hole in it. It's got a load of P on each side. So this is normal stress. So if I didn't have the hole in here, the stress would be this force times whatever this cross-sectional area is. However, what we've got is a hole here. And so the stress concentration factor of this hole, we need to compute what that's going to be. So you can imagine this force is going to be going, it's got to get to the ground, right? We know that the load is going to travel the path of greatest stiffness, greatest resistance. And so this load is going to start off being evenly distributed on this right side here. And it's going to be evenly distributed until it gets closer to this hole. And the load is going to magically know that it can't go through the hole because there's zero stiffness at the hole. We're going to turn the corner and then it's going to go up here. And so we're going to have, it's like water flowing down a river. It's going to flow nice and smooth here. But when it gets close to this hole, it's going to rush around. It's going to cause that stress concentration factor. And then it's going to settle back out to this other shape. So this, in this example here, let's say we've got a parameter at the bottom. Let's pick a good number here. Say this is 0.1, 0.2. So say 2 times r divided by the d. Say that's 0.15. So it would be on this vertical line here. And so what I do is I find 2 times little r divided by big D, and then I go up on the curve. If it's 0.15 is the number, I go straight up until I hit this red curve, which is right here, and then I go to the left over here, and I see my K factor is 2.6. So again, the only thing that matters is this geometry. R is part of the geometry, is this radius. D is part of the geometry, is the height of this plate. This is not the right picture for that problem we just saw over here. This is going to have a different chart, a different picture in the book. This is for a hole with a plate in it. This is a shaft with a discontinuity in it. So you have to make sure you find the right chart for your geometry and then do that trick. Find where you are on the x-axis and then move up to the red curve and then go left and find the K factor, which in this case, if 2r over d is 0.15, you go straight up and you know the K factor is 2.6. So not too painful. Here's another curve for a flat plate with a transition here with a radius of r, loads on each side. And so depending on, we got 2 parameters here. So I got little r over little d. So this is going to be that radius divided by the smaller distance here. I find out where I'm at there. And then I go up until I hit one of these curves, and these other curves are big D over little d curves. And so you have to find two parameters. One is little r over d. You find where you are there. Say it's 0.14. You go up and up and up until you get to, say here, this is what? This is 1.5. So big D over little d is 1.5. So if I start here at, where was I? 0.14. I go up and I find this point right here, which is big D over little d is 1.5. Then I move over to the left and pick off my K factor. So you can see it depends on what the ratio between big D and little d is, and it depends on the ratio between little r and little d. And if you've got a big D over little d of 1.4, you'll have to interpolate between these two curves. So you can handle that. So that's how we calculate the stress concentration factors. There's a whole family of these charts in the back of the book. So you can see those when you work on the homework problems. All right, so here's the homework for next time to work on. We've got, you've been working on this already, the first parts of the problems. Now we've gone through the whole set of lecture notes. Now you should be able to work the rest of these. So these are due next week. If you have questions about the homework, come see me in my office. I'll be here tomorrow in my office, or you can send me an email question. If you ask a specific question, I can give you a specific answer. If you just ask me, how do I work problem 2.97, I'm not going to answer that with an email. If you come by and visit, we can talk about it and get more in-depth about it. So check Canvas for the due dates, and make sure you get that turned in on time. There'll be a hand calculation portion and a spreadsheet portion. So make sure to turn both of those in. Submit the spreadsheet by email. Bring in your hand calculations at the start of class on the due date. So that's all I got for now. Apologize for missing out on class, but hopefully this video will take the place of me being in person, and we'll talk to you soon.